Okay, there we go. And so let's think about the things that we determined about it. One is that if we measure them separately, let's say initial measurement of either shows that the properties, or rather the electrons, if you will, are 50-50. Right, so that means that we can kind of think about it a little bit, maybe that, there's 50 black, 50 white for every 100, 50 soft, 50 hard. Right? We might also want to say that maybe a good assumption that we can make maybe is that, well, there's 50-50 of each. Then maybe that means that there's 25 soft black, 25 soft white, 25 hard black, and 25 hard white. Got two random binary properties. They're all split, so you think all the combos are 25. We show that that's not exactly how it works, right? These things, right? We can't, right? The next properties that we've noticed is that we can't define color and hardness simultaneously. Know that one is black. You lose the information about the softness or the hardness, and vice versa. Right? So the properties are 50-50, right? But each property, or sorry, let me start that over. Both properties cannot be determined simultaneously. Right? And we saw that because our third observation is that when you define color or hardness, say C, you lose H, and vice versa. Right? So it's not really fair to say that we have 25 of each combination. Because what happens is that if we say we filter out the black ones, and then we measure whether they're hard. Right? So let's say we take some black ones and then we put them through the hardness and take out the hard electrons, right? Only keep the hard electrons. Well, what's the color of those hard electrons? Well, it's not black anymore, right? Because when we measure the color again, these get 50 black, 50 white. We lose all the information about the color. So it's impossible to say that we have simultaneously defined color and hardness. The moment you know one of them, you lose the information on the other. So there is no such thing as a soft black electron. Cannot ever measure exactly a soft black electron because these two properties cannot be determined simultaneously. So we can say one or the other. We can say that our electrons are black and white and work with them that way, or we can say that they're soft and hard, work with them that way, but we can't do both at the same time. We can only pick one. Right? So the question is, so the big question is, again, what we've done is describe what the electrons look like after we touch them. Right? We're manipulating these electrons somewhat by moving them through these black boxes and filtering and discriminating between the different types. So the question we should ask is, what must be the initial property of the electron before it ever goes into the system? Right? What is the representation of the color and the hardness of the electron before it ever enters the system? Before we even look at it, right? What's the initial state, if you will, of the electron? And the only thing that agrees with the experiment is this. Right? It must say that the initial electron, but we'll just kind of write it as the initial electron before anything happens, must be simultaneously black and white. So the initial electron, if we were to represent it as a function or something, just a label, it's not that the electron is black, 50 of them are black and 50 of them are white, but they're all black plus white. So the real original state of the electron looks something like this. I'm going to put it approximately because it's not perfect yet. But the only way for all of this to work, right, and next week's problem set will allow you to explore this, right? We'll actually work out very, very simple math to talk about it today. We actually have two math for problem set one, where we'll go through the math of this problem, very simple, just multiplication. And we'll show that the only possible initial state of the electron that satisfies all of the experimental results that we showed is that the initial electron has to be both simultaneously black and white. It has to be both. And it's even more stringent than that, right? We can say something about the color. This tells me nothing about the hardness, right? Or the softness. Right? So there must be an equivalent description of the electron in the hardness. Right? So we'll say that this is the color representation. But there's an equivalent representation of the electron. Call that, we'll put a C here. There's another initial electron state for the hardness that we could also equivalently represent the electron as the soft electron plus the hard electron. Okay. And you can choose as a person, as an experimenter, which perspective you would rather have about the electron. It can be black and white simultaneously, or it can be hard and soft simultaneously. But you can only choose between one of them. The moment we define the system in terms of its color, we know nothing about its hardness, and vice versa. Right, so these are two equivalent descriptions of the electron from two different perspectives that don't commute. They don't interact. And so you can't know them simultaneously. So these are independent representations of those electrons, depending on the experimental context we choose to identify. Right, so you can kind of say that these are both true, but not simultaneous. Right, so these are only not simultaneously true, one or the other. Right, you can pick one or the other, and when you take one, you lose the other. We can represent our electron, we can measure it, and just know that it's black. And then it's soft. The hard black electron in the hardness characteristic is soft and hard. We don't know anything about it. Okay. Likewise, if we pick that the electron is soft, then its color representation is black plus white. We pick it to be black, know that it's black because we measure it, and its hardness is soft plus hard. All right, so you can never pick, and we'll prove this in this class, that you can never identify an electron that is simultaneously soft and black, white and hard, and so on and so forth. The combinations are impossible. You know one, you don't know the other. If I have this, my hardness is always this. If I have this, my color representation is always the sum of the two. It's even more stringent. As we'll see, it's even more general than this. Because I've plussed them together. Like I've said that the electron is a sum of the black and the white. It turns out, as we'll see, and you'll look at this in the problem set, there's actually plus or minus. You can have a black minus white electron and a black plus white electron, and they're equivalent. They have the same physics, but they're two different representations of the same electron. And in fact, you can do special experiments where the plus combination might go one direction, the negative combination goes in another direction. So it's incredibly general. It's not only that it's a sum of the states, but also could be a difference in the state. It's even more general than that, right? The fact of the matter is that the proper representation of our electron, before we ever touch it, is that it is simultaneously, if you will, all of its properties. It must have all of its properties. And the only time that the property is assigned is when we measure. Okay? So the act of measurement, by putting it through our box and filtering it, is what causes us to identify a black or a white electron or a soft and a hard electron. But so we can identify with our experimental measurement whether electron passes through, whether it's black or white, and it's random, it's 50-50. But before that happens, the only way for that 50-50 to work out in all the math is that initially it has to be both at the same time. There's a term for this. This concept, this is an extraordinarily important part about quantum mechanics. I call this principle one. Which is called superposition. And we'll formalize this next week, but I just want to talk about the fundamental principles of quantum mechanics, the properties that our systems have at the microscopic level. One of them is superposition. And what that means is that, so let's say we have a particle or a system represented by states, let's say a set of states or a set of labels that characterize each property, result. Each result, potential result of our measurement. Right, we have a white and a black, for instance. Right, we'll call those results. Right, so the potential results, well, these are some kind of notation. By results, I mean, what are the states that we observe, black, white, right? They could be, for instance, we'll use this letter phi, be phi 1, phi 2, and so on and so forth, where, as example, we have for color phi white and phi black. Okay. Imagine that you have, these are like little functions. We'll actually characterize these are actual functions. Things that map. But imagine that we have that our electron can be represented by some mathematical labeling, some sort of function, anything you think of. It just be a symbol. Right? And each of our results, white, black, hard, soft, can be written as a separate function. We can show always that the most general solution to the problem, the most general representation of the system, is the sum of all, or the difference of all the possible results. All right, so the electron in this case, we represent as a what we call psi. Right? We have a term for this. This is what's called, we haven't defined this yet. This is what's called a wave function. And the wave function is going to be a sum over some number of possible results, however many there are, equals 1 to n, of a number, c sub I, times phi I, right? Where, and this is very stringent, the sum of the squares of all of these numbers, which are real numbers, has to equal 1. So we have the idea is that this is the electron, if you will. This is our representation of the electron, the wave function, this psi. And it equals it's just a function that's a sum of these smaller result functions. Right, so let's just do a quick example, right, for the electron. And we'll work out the math on this as we go through the class. Again, we don't know exactly how to work with this yet, but we will. But for the electron with color, we would say that the electron's wave function for color turns out to be, and we'll derive this later, 1 over the square root of 2 times the function representing the white electron plus or minus the 1 for the black. All right. Now you may wonder why this is 1 over the square root of 2. Why do I put this here? Well, the coefficients on the outside of each of these functions, these C numbers, they have to sum to 1 once you sum over all of them. Squares of them have to sum to 1. Right, so let's just double check that. The coefficient on the outside of the white function is 1 over the square root of 2. Square that, that's 1/2. You have another 1/2 over here. 1/2 plus 1/2 is 1. Okay. All right. We'll understand very soon why this has to be 1. Okay, but that's just a rule. All right. This is the most general, from our perspective, the most general representation of our electron going before it ever enters the box. The only way for all of this math to work is to assume that the functional form or the representation or symbol of the representation of the electron is that it's simultaneously white and black with equal weights. There's an equal amount of white character and an equal amount of black character. It's on the outside, it's 1 over the square root of 2 on both. They're equal. And this, well, as we'll see, this equals, this means that when you measure color, as we'll see, when you measure color, right, with the color box, you guarantee to get 50% white and 50% black. This is the only way, mathematically, that you get this result, and everything is consistent. There is an equivalent form of this wave function where it's hardness instead, where you have this is hard and this is soft. And we can maybe potentially think about what the wave function looks like for something that's completely undefined, no color, no hardness. You can't do that because you can't describe a system in terms of its color and its hardness simultaneously. Have to make a choice. No one, you don't know the other. So there's no really way for me to write it in a consistent way a function that both characterizes its color and its hardness simultaneously. Right? I could just pick one or the other. Have to make a choice. Right? So we can use an experiment, right? Depending on the context of our experiment, we're working in the color world or working in the hardness world. That's an experimental choice that we make. And our mathematical representation of the electron has to correspond to that decision that we make in the experiment. All right. The important thing that we're going to really focus on is that, again, it should be problematic in your head that we have this particle, this electron, that moves in a straight line like a bullet. At least that's what we think it does. Feels like a normal particle or a billiard ball moving around. But it's simultaneously all of its properties at all times. You have a problem. And so what we're going to have to understand, this is one of the tricks and kind of the logical steps that we have to do when we talk about microscopic science, is that this is a representation of the electron from the perspective of our experiment. It tells me in some ways nothing about what the electron actually is physically. It just tells me something about the results of my experiment. Like this is a representation of the statistics and the results I see in my experiment. The moment it turns out that then you say, okay, well, what's the true nature of the electron? Right? If this is just a experimental explanation, a way to describe the electron and its results experimentally, like a representation, not its true nature. You could say, okay, well, there must be another description, a hidden description of the electron that tells me truly how it works. Right? That makes more logical sense in my head, where a particle obviously can't be both white and black. Right? That doesn't make sense. There must be some hidden description that we don't understand. And all we're doing is just describing the results of our experiment. People have tried that. They've thought about that problem, right? The disconnection between reality and the fact that we're making a measurement. Right? And that this wave function just represents our measurement result. It doesn't actually represent the electron itself. And the electron works totally normally, but our experiment gives us this uncertainty. And people have tried this experiment in multiple different ways. Time and time and time again, it proves that there is no hidden theory. There's nothing hidden that solves these problems. As far as we can tell, this is how the electron is when we measure. There's no way of getting around it. Fact of reality and the fact of nature. So it's not like we're having this issue understanding our experiment and we're coming up with this crazy logic to get around these problems, and that we're just not smart enough to know the true answer. We just know how to model the results and formalize that question. Time and time again, physicists have shown this is the correct description of the electron. Very, very strange, right? So we'll have to formalize this idea of a wave function. Why is it that these coefficients sum to 1? But you can say, okay, well, again, if you think about it, we know that probability, for instance, is 1, right? If you have the probability of any event happening, given a certain set of events, chance of any event happening, 100% chance something is going to happen. And so the idea here is that these coefficients tell you something about the probability of observing. And so the sum of all the probabilities squared has to equal 1. That's our restriction here. And that makes sense, right? If we square these numbers, they're 1/2, 1/2. The probability of 1/2 is a 50% chance, right? So these numbers have something to do with the probabilities of detecting whether a white or a black electron. But we'll formalize that. There's some statistics in these numbers. And we're going to see that statistics, averages, and things like that are intricately connected to this structure. The best we can do in quantum mechanics, we'll see, is to calculate averages. Because the system, the electron itself, physically is undefined. And all we can do is calculate probabilities of whether when we define the electron by measuring it, it's white or black. Very, very strange. Let me show you an example that maybe is a little more clear of this idea of superposition. Because these are binary properties, right? Black, white, hard, soft. Can we maybe come up with an experiment where we see this kind of non-simultaneity, right? The fact that we can't know color and hardness at the same time. Can we do that with a property that's continuous? It's something that has many values, infinite values, something that we can kind of track in time, for instance, right? Well, imagine we can watch an electron move along. There's a way we can watch its motion, for instance, and see that there's maybe this superposition concept, these different types of properties that can go at the same time, or anything that we can do that's continuous that allows us to visualize it, right? Instead of just ones and zeros, let's do it smoothly. This is a really great experiment I'm going to show you guys. And this is an experiment, if you have a good laser pointer and you're pretty good with construction paper and cutting and stuff, you can actually do this experiment with light. Bring this over to the screen. I want to show you an experiment that maybe you guys have heard about called the double slit experiment. This is another example of this indeterminacy between two different properties. All right, so let me show you what I got. Let me change this to laser. Put two slits. Okay. So let me explain this experiment. Raise your hands. Anyone ever heard of the double slit experiment? Okay. this will give us the same, this gives us the same conclusion. Now we're looking at different properties in color and hardness. I'll explain what those properties are in a second. But we'll see that we get the same consequences that we got in color and hardness that we make here in color. All right, so what's going to happen? I have a laser here. Right, that should be 500 amps, a green laser. I can change the frequency I want, doesn't matter. Right, we'll see that, and then what we're going to do is we're going to make a barrier here, a narrow barrier that's got two small slits, where the slits are much smaller than the wavelength of the light. Well, they're about the slit, so they're separated by 1500 nanometers, and their width is the same roughly as the frequency of the wave. Okay, so what's going to happen is the light's going to propagate. Let's take it slowly here. Might as well restart it. Right. The light's going to propagate. At this scale, light just looks like waves like this. Right. So these are the frequency of the waves, and it passes through these holes. And what do you see? Well, so you have this, what we call a plane wave, right? This is what a laser beam looks like if you were to zoom in really, really close. Right. It looks like alternating peaks. It's just a wave like this, right? These are the peaks of the, and these are the troughs of the wave. And it moves and lasers are spatially coherent, which means all of the light is moving in the same direction, the same phase. So you have this big block of waves coming in, right? That's what it looks like. It's called plane wave. And what happens is that this light gets jammed into these two things here. And what happens is that you've broken the plane wave behavior of the light. And the light has to come through, when it comes through these holes, it makes these kind of circular ripples, right? These are called Huygens fringes, where they propagate outwards like water ripples, right? It's kind of like you have this piece of energy here that's moving in, and then you drop a rock here, and you're building ripples out of that propagate out of the holes. Okay, let's just keep watching it. And you can see that, right? So this is just, you can do this with a laser pointer. And you have to be pretty good at sharing. Cutting, if you get some nice slits to get it really dark, you can reproduce this. My optics professor in graduate school did, of course. And so let's think a little bit about what do we see here. Right? Imagine we have a screen here, a detector. What do we see? The intensity pattern on the screen. So let me turn that on. So what we get are these fringes. You can see now that we've gone from having this straight moving plane wave to having regions where the two waves that propagate out of these slits either constructively interfere, which means that the peaks of this wave hit the screen at the same time the peaks of this wave hit. And then there are regions where the peak of one hits the trough of the other and they cancel out, right? You have constructive and destructive interference of the waves. And they're spatially separated, right? So you get this kind of oscillatory pattern of regions where the two waves hit the screen at the same time, at the same phase, and other times when they're out of phase 180 degrees. All right, this is a classical effect, right? This is not quantum mechanical. Well, it is quantum mechanical, but people knew about this before quantum mechanics existed. Actually, Huygens, long time ago. Right, and you can see that the pattern is this like sinusoidal thing, and there's more intensity in the middle. That's kind of where the most intense parts of the wave kind of meet, and then it kind of fades out. All right, so that's light. Now, what if we instead take instead of a light generator, we take an electron gun, and we run electrons? Let's think about it. So instead, what we're going to do is, again, we'll have an electron gun here. And the gun can shoot the electrons out at high speed, low speed, different kinetic energies. It doesn't really matter. And we're going to, and maybe what we'll do is we'll at very far distance, Right, so we'll take a really long distance. And then eventually what happens is that we'll have two slits. Like this. Okay, and let's say, for instance, that the electrons, let me just say the electrons have a bit of a spread, right? So they're not perfect bullets, right? So let's say the electrons kind of, on average, kind of distribute out like this. And they propagate some distance. Let's just call it L. And then they had a screen. Right, this is our detector. So let's do a really, really simple experiment. The first thing I'm going to do, the first experiment I'm going to do is I'm going to close one slit. So I'm going to put a wall there at 1, right? So the electrons can only pass through the first slit. Now the question is, what do I see? People do this experiment, and it shouldn't be that interesting, right? The electron has only one path to the detector, right? So the electron is just going to fly out of here, just move on, and then jam and hit the detector. Right? So what do I see on the detector? Well, what I see on the detector is my detector output. Let me just kind of mark where the slits are. So here's one slit, and here's the other slit. That a little more symmetric. Use white specify where the slits are. On the detector, I see literally electron bullets. I see a spread of electrons right around the first slit. So what I would see here is a pattern, depending on how sharply focused the beam of electrons is. Right, you see basically a spread of targets, right? So the electrons are like bullets here. And again, I can swap this over here and I see the same thing, right? If I change the slit, it doesn't matter. I get what's down here instead, electrons down here. Now, I'm going to show you the answer when I take that slit cover off. What do I see? Well, I take this off, right? So now, I'll write 2 here with an X, which means it's open. Both slits open. Well, again, I don't know anything about the electrons before the slits, right? All I do is I shoot them out. And I know that they're moving in some distance towards the detector. But they have a choice, right? Some electrons, everything is symmetric, 50% of the electrons that pass through the slits will go through the bottom one. 50% maybe will go through the top. So they have a choice now. So our expectation, right? So let's do our experiment again, right? Let's think about what happened in experiment 1. If slit 1 is open by itself, see a target pattern that exhibits the properties that the electrons are acting like particles or bullets, billiard balls. And if we change the slit, you see the same thing, just on the other slit. Right, so now what I do is I just take that shield away. And now the particle has 2 choices to go through. Right? It can go through 1 or go through 2. All right, so if these were billiard balls or actual bullets, right? This was an actual bullet, right? You would see now patterns at both target bullet patterns, or bullet sprays at both slits. Right? If they were pool balls or 9mm bullets. But what you in fact see I'll do my best to reproduce the result on a piece of paper. But what you see instead, let me do a different color, the red. What you see instead is an interference pattern exactly like you do for light. So when you have the electron now has a choice to go between the two, either one of those splits. They no longer act like bullets, they act like blades that interfere with each other. Exactly like blades. Precisely like blades. They have the same property that light does when it goes through them. All right, and you say, okay, well, so we've gone from the situation, right? So let's go back to the color picture that we had. Right, in the color picture, we had electrons that are black and white, right? And if we didn't know one or the other, they were black plus white. Right, so the first interpretation that I have here is that when I make a choice about which split the electron goes through, I force it to go through one, I have defined that electron as passing through one of them, right? The electrons that go through here are all slit one electrons. And if I open slit two, all the electrons are slit two electrons. But if they have a choice, I haven't made any sort of determination about their characteristics of their position and their momentum. So the only way that this could happen is that the electron is both simultaneously going through two and one. That the electron is slit one plus slit two. Right? That's the only way for electrons to interfere with themselves, is if the possibility is that the electrons are actually propagating through both of them simultaneously. Just like light. Right? So what this tells us is that from this perspective, from the detector, right, experiment 1 says that the wave function for our electron is this phi of slit 1 or phi of slit 2, depending on which one you choose. In experiment 2, the only explanation that we have for this is that the electron must be represented as one that passes through slit 1 plus or minus slit 2. It's gone through both simultaneously. Now, you may say, okay, well, maybe that has something to do with my detector. Right? Because I make this determination of whether I'm in this region, right, where I know exactly what slit it goes through, and where I have to insert it. That occurs precisely at the detector. Right? I don't know anything about the electrons. I don't know how they're moving until I detect them. So maybe this determination is made at the detector. All right, so let's try something a little more clever instead. Maybe the problem is that we're using this screen. Maybe we should have maybe there's a better way to detect this. So, and this is a thought experiment that Richard Feynman came up with. I think people have done this experiment before too, where instead of detecting the electrons on the screen, I'm going to put two little light bulbs at each of the slits. Two little light bulbs. All right, so this is experiment 3. Let's go down a bit. I'm going to put two little light bulbs at each of the slit. All right, and what's going to happen is that if an electron comes through slit 1, the light bulb for slit 1 flashes. Right? It's like a little motion detector. Well, And if it passes through slit 2, you know that it's gone through slit 2. Okay? There's no imaging at the end. We're just flashing a light every time there's a voltage that passes through the slit. Right? So light turns on. That switch when it detects a current through the slit. So what happens when I do that? Well, I turn on the electron gun. Maybe I start just slowly tapering the electrons out, occasionally, and one electron passes through. Let's say light bulb 1 flashes, come through here. The next one comes through. This one flashes. Maybe this one flashes the next 3 or 4 times, and so on and so forth. Do that, and we just keep flashing, right? Right, and it seems like when I do that, that they move like particles. So I see, and then if I turn on my detector after the fact, just to double check that, I'm going to look at my detector at the end. So I was going to say both lights flash discretely as electrons flow. And the detector result that I see, put it over here, is very consistent with the result that I have particles moving through 2 slits, and there's 50-50 of them, and some of them end at the bottom slit and some of them at the top slit. So it has nothing to do with my detector. Same result as experiment 1. Same result experiment. So even if I make my detector, and it's even worse than that, right? So maybe the problem is that my light is too bright. Like the fact that my light is flashing, it's too obvious of a detection. Right, so let's make it even less sensitive, right? So let's turn the light bulb down, make it dimmer and dimmer and dimmer, so that the light bulb barely flashes when an electron moves by. Barely flashes. Can't even see it yourself, maybe. Maybe you have to look at it in pitch dark room and magnifying glass would sit there with your eyes to adjust to see it. So you're doing a very, very weak detection. Weakest possible detection you can think of. So weak that you barely see it yourself. Still see the independent of the intensity of that detection. So it has nothing to do with the detector. You can have a great detector that's super sensitive. You can have a terrible detector that sometimes misses electrons even. It's not even sensitive enough to pick up the flux of electrons. Maybe it misses half. No matter what, the fact that you've made that decision to detect whether something moves through slit 1 or slit 2 has been chosen, and you always get this result. It's independent of the detector. But the only answer that we have is that the electron must be going through both slits simultaneously. It's the only way to describe the results. And I could prove this. Because what did I say? So what are the two possibilities? One that can act like bullets, particles, or they can act like waves. Right? Is there perhaps a way, maybe we can be really, really precise and watch electrons hit a screen. And maybe if we average long enough and we have sensitive enough detector, maybe we can see some hybrid of these 2 results. Maybe, in fact, as they start to hit the screen, and we just average over all those particles, eventually the wave behavior starts to appear. So let me show you an example. This is an actual video from, I believe, Hitachi. I don't remember the exact story of this video. Okay. But I think it's a beautiful video. Here it is. There. Let me put this YouTube video up on the screen. All right, so I think this came from Hitachi's research labs in the 1990s. I think they were working. I don't remember exactly what they were doing. It has something to do with digital media technology, and they built this basically a single electron gun, shoots one electron at a time, and they build a detector sensitive enough to pick up a single electron signal. Very, very sensitive electron. Yeah, very, very straight stable. All right. And this is a real video, a real experiment. All right, so this is a picture of the detector plane on the other side of the two slits. I think there's multiple slits in this experiment, but it's the same concept too. Right, you can see, right, the electrons, right, they hit like particles, right? We have a detector, and they just, I think it's maybe 5 slits or something like that, but the result is still the same. It doesn't matter how many slits you have, just options, right? And you can see, right, bullet, 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 bullet. Right, and these electrons constantly hit the bullets, right? They're detected one by one as particles. We have to conclude that each electron must have passed at random on each side of the prism. Oh, this is a prism, it's a little different, but it's the same concept. And creating a uniform distribution. Right, you can see that, it just looks random. Just random bullet hits. But under these conditions, right, they ask, is it actually uniform, right? So they keep pumping in more electrons, random electrons. And what do you start to see? It's a little hard to see here, right? This is 30 minutes. You can start to see there's some structure here. Right? It's not a random distribution, right? If it were just particles, right, it would look kind of like a bell curve, right? A kind of a spherical distribution, right? It would be just kind of random. It would have a mean and some average variance around the center of the detector. Well, or in the case if there's no, or rather it might be just completely dispersed and random, like noise, right? Like snow. Right? But what do we see? As you start to accumulate more and more bullet shots, you can see that there are specific regions. Right? A little too far. A little hard to see because of the resolution, but you can see there are regions here where it's a little darker. And then there are pockets or strands where it's brighter, where there's more electrons hitting. This is the exact same interference pattern that you get with light. So what this tells me, that electrons can do both simultaneously, right? They're particles, since they hit like bullets, but statistically, every individual event here is a bullet hit, but statistically, they don't hit like bullets, right? Statistically, they hit like waves. There's no wave property. This would just be random snow. But instead, you get these Huygens functions, interference pattern, which can only happen is that if you have 2 different waves coming out of each of the holes, each of the slits, and interfering at the detector, like waves. So what does that tell me? Right. So the conclusion of this experiment, the lesson that we learn here, is that electrons, or we can, in fact, you can do this experiment more with electrons. They did it with atoms, light, obviously. In fact, people have shown the particle nature of light through this as well. Of course, light's generally treated as a wave. You can set up an experiment to show that photons move through the slits like particles as well, if you set it up just right. Everything works right. Atoms, molecules. People have done this with actual molecules. And it has the same result. Electrons are any microscopic particle. Simultaneously acts like a particle and a wave, right? It collides with the detector like a particle, but the way that it macroscopically accumulates hits is like a wave. So it has wave and particle properties simultaneously. So the question you may ask now, we don't quite have the answer to this yet, but this is a question of superposition, right? We've already seen this, right? That the only way for this electron to act like a wave is that if it's simultaneously going through slit 1 and slit 2, interfering with itself. But what are the properties that are not compatible, right? What is the property of a system that represents itself as a particle, and what is a wave, right? What is that, like color and hardness? You know, what are the color and hardness equivalents? Right? What particle mean? What does it mean to be a wave? And we're going to answer that question. It's one of the most important questions in quantum mechanics. So the way to think about this, and we'll come back to this next week. The idea is that particle-like behavior what does that imply about our knowledge of the molecule or the atom? Well, this means that we know the position x, y, z of the particle exactly, right? We can track it like a particle, right? So we're when it goes through slit 1, we can basically effectively we can trace the physics or the Newtonian physics of that electron traveling back through slit 1 back, right? So we know where x, y, z is at all times, right? Just like a billiard ball or a bowling. We know position. That's the key word here, exactly. So what about the wavelength moving? What is a wave? Well, obviously a wave has no defined position because it's delocalized across the entire detector, right? There's a wave here, there's a part of the wave here, right? It just continues on forever, right? So there's no position, right? Position is undefined. Right? The electron appears almost everywhere on the detector. Wait, completely delocalized, right? But what does a wave have that's fixed? Wave has a wavelength that's fixed, right? So it has a well-defined wavelength, right? But a well-defined wavelength, and what we're going to see in the next week is that this is equivalent to having a well-defined momentum. Remember that momentum P is the mass of the particle times the velocity of the particle. And in a wave, this is for a particle, but for a wave, there's an equivalently formed momentum that we'll talk about. It's called the wave vector. And for a wave, I think so. The equivalent is what's called k, and that's 2 pi over the wavelength. So momentum and wavelength are associated with each other for a wave. We'll talk about that. That's important here. But the idea is that when a particle, when the particle goes through a single slit, we know its position exactly. See it as a dot, right? As a polar. But we don't know anything about how the particle is moving, right? If you go through either slit, we see it as a wave. And what that means is that we lose all the information about the position, but we know exactly the wavelength of the wave equivalent of that. Right? Its momentum, how fast it's, how much energy it's, how much inertia it has, right? And that's dependent, again, in waves on its wavelength. All right, so what that means is that the conclusion for this is momentum and position are not simultaneously measurable. We can choose one or the other. We can either talk about something and where it sits, or we can talk about the energy content itself, or its momentum. Maybe if it's motion, think about it. Velocity. Velocity will not be a particularly useful thing for us to talk about. But the important thing is that momentum, this is kind of like the wave momentum in space, is related to the wavelength or wavelength of the electron. Electron has a characteristic wavelength associated. We'll have to think about what the wavelength of an electron is. In fact, every particle, even Charlie and Allison, every one of you have a characteristic wavelength. Because you are also, in some sense, a quantum particle. You're a composite particle of many particles. And you have a very well-defined position and momentum, obviously, because you can see that I'm here and you know exactly how fast I'm walking, right? So classical world, you can measure both of these things simultaneously. But what we're going to see is that there is some inherent uncertainty in our momentum as we know our position. So if Allison tells me she's standing exactly on the square right here, there is some inherent uncertainty in what her momentum is. She's going to tell me it's zero because she's not moving, but there's going to be some uncertainty in that from quantum mechanics. But that uncertainty is tiny, absolutely tiny, because it's dependent on the size of the system. So when you're microscopic, that uncertainty is as large as the value it is. It's undefined. But when you're large, that error is a very small fraction of the actual size. You don't really worry. But when we get to things that are on the size of an electron or an atom, those errors are basically to the point if you know the position, you don't know the momentum and vice versa. And what that also means is that if you know the energy, your position is completely undefined. So when we talk, for instance, about electrons in the hydrogen atom in the 1s orbital, when we say an electron is in the 1s orbital, we're giving it a specific energy and momentum. And what we find is that the position of that electron is completely undefined. It's everywhere around the proton. Right? Remember, the 1s orbital is like a sphere around the proton. Right? And that sphere represents the position representation of the electron in the 1s orbital. And what it says is that if we define the momentum exactly, which is to say, hey, 1s, then we don't know the position. In that situation, the position is a sphere, fully undefined. Likewise, if we say, hey, this electron is due north above my proton, relatively north of my experiment. Imagine I put the electron, I localize it, or pole on hydrogen. Then I lose all my information about its energy. In fact, a particle like that is at multiple energy. Momentum has multiple momentum. Right? So just like before, remember, if we define something to be black, we don't know it's hard or soft. If we define something in a specific position, then its momentum representation has many different momentum, and vice versa. And this is even scarier because position and momentum are continuous variables. Right? They're not binary. It's not position one, position two, momentum one, position two. They're smooth. Right? You can particle here, all the way up to infinity. And momentum from zero all the way up to infinity. Right? And these are not simultaneously measurable either. We're going to find a big long list of things that are not simultaneously measurable, but there are things that are measurable together. Right? That's going to be the trick of this question thing, is that if we don't know anything about our system, can we find groups of properties that we can measure together? Right? For instance, as we'll see, we might not be able to measure momentum and position together, but we'll see soon that you'll be able to measure energy in position. Or momentum and energy, but not position. There's going to be combinations of properties that we can measure together Combinations of properties we can't measure. And so we're going to have to find the ideal context for thinking about chemistry. What are the trade-offs we're going to have? Think about orbitals, for instance. We're going to get rid of position altogether. We want to think about energy. Energy. And when we do that, we're going to lose a lot of information about the position, vice versa. Okay. So again, this is all about superposition and uncertainty. Right? So the first principle is uncertainty. All right, how much time do I got? All right, let's look at one more thing for the last 10 minutes, and then we'll finish it up on Tuesday. This will get us to right about the right place to start thinking about the principles of quantum mechanics and the different rules. How do we define systems? So I just want to look at one more cool experiment. A nice picture for you for this, and there's no app. So let's talk a little bit about light for the last 10 minutes. So what I want you to do is to imagine, I think about the coils in your oven. What happens when you turn the heat on in your coils, right? They start to warm up. Eventually they get so warm that they start to glow red. You know, or if you think about fire, for instance, the more blue flame, the hotter it is. So connection between light color and energy or heat. Now what I want you to imagine is, again, your oven or some sort of box that you can heat and it emits radiation like an oven. And all of that radiation and any sort of incident radiation that comes in, say, from the sun or your energy source is 100% absorbed, not reflected, but absorbed by this body, say the oven. Right? There's no reflection. Okay? So it's what's called a black box, something that doesn't reflect any light. It absorbs all the radiation and then re-emits it as heat or as light. Called black box, right? A great example of a nearly perfect black body is the sun, for instance. Sun absorbs radiation, it doesn't reflect, and it emits its heat as light or an oven. Right. And so when you do the math, we'll kind of go through the math hopefully on Tuesday. Let's kind of show you characteristically what you get. Is that you can choose, what you find is that that these bodies, like your oven, depending on the temperature, actually emits one wavelength of light, but many. Right? And so this is what's called a black body spectrum. And so you can choose, say, for instance, let's choose the temperature of our materials. Let's go to a light bulb, for instance. Right, and I'll show you the math of this in next Tuesday. We might not even talk about it. I think it's better to put it on. Yeah, we'll talk about it. And what happens is that as a function of temperature, you get this curve here, right? And this tells you what's called the power spectral density, which tells you how much power, how much energy this box or this oven radiates at a given wavelength. So it's set up here. So this is all the infrared here. This is the optical region. And I've set my temperature to 3000 Kelvin, which is like an incandescent light bulb. And you can see that, in fact, most of the radiation that a system emits is in the infrared here. Right? And if I start to increase it towards the sun, right, the peak starts to be in the green. The sun actually is primarily a green emitter. But you don't see that because your eyes can't. It looks like white. And your eyes are more sensitive. So you don't see it as green, but the majority of the light, the most intense light that the sun emits is. Right? And so what happens as a function of temperature, the peak of this distribution of the light that gets emitted changes. So as the temperature goes up, the light that comes out becomes more and more energetic, right? Wavelength, this is more energetic, higher frequency, lower. And you can see that, right? So for instance, on Earth, you can see that the peak of the Earth, at the Earth temperature about, well, that's like not even close to the Earth temperature, that's more like Venus. Peaks in the infrared, right? This is about 6 microns. That's in the infrared. Right, that's why the Earth doesn't glow for us, because most of it's like, there's no visible light being emitted from a 300 Kelvin body, all the light's in the infrared. So if we had infrared eyes, the world would glow to us, right? Just like all of us would glow as well. And this is just a smooth function of the energy, right? If I go up to the sun or Sirius A, which is a really hot sun, with one of the largest stars in our galaxy, or visible galaxy, you can see that the majority is in the ultraviolet. And Sirius A is a bright white, bluish star. Very bright white. Okay, so we're going to work through this math just a bit on Tuesday. But here's an interesting thing. It's that this people have been studying this curve for a very long time. And so what people used to think before quantum mechanics appeared, the idea of things being quantum mechanical, microscopic, they used to think, okay, well, every atom in your oven, right, is a little oscillator, a little thing that vibrates a little bit, and as it vibrates, it emits radiation. Think of it like a little spring. So every atom's a little spring, and the frequency at which the spring vibrates, it corresponds to the wavelength of the frequency of the light. And so people thought, okay, well, let's imagine that this black body, big collection of these little springs that emit radiation at their frequencies. And again, they're just like normal springs, right? So we can set them to any frequency we want. We can give them any amount of energy we want. We can make any choice we want. How much energy each oscillator will have at given time. Right? They're equilibrium of each other. They're all oscillating at some temperature. And they can emit any energy or any amount of that light that they want. So their brightness and their frequency or their wavelength is totally universally good. All right, so when you work with that math, that's a very logical math, right? So oscillators that are emitting light and any energy or anything. What happens when you do that math is that at low energy, you get this curve, all right? So I'll show you this curve next class, but you get this behavior right here, right? And it says that the intensity of the light increases as a function of wavelength at a given temperature, right? So it's weak here and it gets stronger and stronger and stronger, right? And we see experimentally that it peaks down like this. Right? Eventually it rolls off. But when you do that math, that every little oscillator inside of that oven can emit any amount of energy of radiation it wants at any frequency. When you do that math, this curve never goes down. In fact, the curve just keeps going up and up and up and up and up and up to infinity. It diverges. And what that would mean is that anything of any temperature would glow white hot with infinite energy. The moment you put any energy into a system, it would glow white hot because this power density, the spectral power density, increases monotonically with wavelength. The wavelength goes down, and you get more and more energy and more light as you get more and more blue. All right, so the claim is that every object at any temperature should glow infinitely bright. Well, that's obviously not true. Experimentally, they already knew that it looked like this, right? Their curve kind of looks like this, and it just kept going and going and going. Something's wrong with the computer. So what we're going to talk about on Tuesday, for just very briefly, maybe 10 minutes, 15 minutes, is that a man named Max Planck came up with a different approach to this problem. what he said was each of these little oscillator atoms, each of these little atoms that are vibrating and emitting light, they can emit light at any frequency they please, the wavelength they please. That's fine. We see that, right? We see some light in the infrared, some in the visible, and some in the ultraviolet. Like we know that it emits in all the wavelengths. But he makes a very specific assumption. He makes the assumption that each of these oscillators can only emit the light in little discrete packets. So you can't emit 1.2 units of light or 6.35 units of light. You can emit 1 unit of light, 2 units of light, 3 units of light, 4 units of light, 5 units of light, and so on. Right? So you can't do anything in between. So what that means is that the energy is discrete. You can have 1 unit of energy at that frequency, or 2 units of energy at that frequency, or 3, but nothing in between. Right? And what that does is it changes this math, as we'll see, from an integral over energy to a sum over energies. We don't have a continuous function. Now, by one, the y-axis, if you will, is 1, 2, 3, 4, 5, 6, 7, 8, and nothing in between. So it makes the assumption that each little oscillator can only emit 1 packet of light or 2 packets of light, or n packets, not n.256. Does that matter? And he reproduces this curve exactly. So he learns something. He learns that light is not emitted like energy, where it can be emitted in any arbitrary amounts of grams or units of light. Think of it in terms of light. Light acts like atoms. There is 1 unit or 1 atom of light, 2 atoms of light, 3 atoms of light, 4 atoms of light, not 4.25 atoms. Right? That light comes in little packets like atoms or molecules. And it turns out that this assumption that he makes is the right answer. This is the other big important results in quantum mechanics. He didn't realize this. Quantum mechanics didn't exist when Planck did this analysis. He just made a guess. He literally made a guess. He had no good reason to make this guess, and most people didn't believe it. He just made it up and hey, it works. And so he calls these light packets quantum, or quantized. Like you can label them. 1 of them, there's 2 of them, there's 3 of them. You can count them. It says that light is quantized. And it turns out that, right, if you think about light, a quanta of light containing a little bit of energy, a little light particle has a little bit of energy. That means that the energy of these oscillators are quantized. You can emit 1 unit of energy or 2 units of energy, not 1.5. Right? So he thinks that there's not a continuous range of energies, but rather discrete energy levels. 1 photon, 2 photons, 3 photons, and nothing in between. So the energies of these oscillators are quantized, not continuous. They take on certain values. And it turns out, maybe that's not that surprising if we talk about orbitals and things like that. Every quantum mechanical particle is quantized. No particle in the universe, except for one. We'll talk about it. There isn't a case where it will be continuous. But if you have a particle that's in a system, say like a hydrogen atom, or you have an electron in a box, or an oscillator bound to a solid, where it can't move, it's just there vibrating, stuck, bound. The energies of that particle will be quantized. There are energies that it's allowed to be at, and then everything in between it's not allowed. Right? There's spacings between the different allowed energies. And Planck calls this quantization. And next to superposition, quantization is the other most important characteristic of quantum. That's why we call it quantum mechanics. Because particles are quantized. Energy is quantized. 1, 2, 3, not 1.1, 1.2, 1.3, 1.4, 2.1, 2.1, none of that. Everything can be labeled with an integer. First energy level, the second one, the third one, the fourth one, and nothing in between. Every quantum mechanical property shares this structure. Energy is quantized, position is quantized, momentum is quantized, color is quantized. It only has 2 choices, but it has 2, not infinity. Hardness is quantized. Every property has is represented as a quantum. You count 1, 2, 3, 4 integers, no real numbers. And Right? That's gonna be a fundamental guiding principle in this class. And when we start on Tuesday, we'll start looking at the principles of wave functions and quantization, superpositions and stuff like that. You're gonna see that information coded correctly. And this will give us a good picture of how an atom or a molecule or a piece of light or anything begins to look like and how it functions at the microscopic level. Okay. All right, so that's all I have for you today. I will post a homework Tuesday. We'll go over the homework Tuesday, I think, in class. I'll talk about the math, and the math in there, very easy. It's about color and hardness. And then we'll continue on this discussion about quantization.
And lab safety training time.
Good luck.
Apparently she's been going a lot faster this year.